I'm Amy, and today I'm going to talk about Flexplane, an experimentation platform for resource management in data centers. This is joint work with Jonathan and Hari at MIT and Peter at Facebook. Data center applications today have diverse requirements from the underlying network. Some applications want low latency, while others want high throughput, and others care about deadlines, fairness, or isolation. These properties can significantly impact the performance of data center applications. As a result, researchers have developed dozens of new resource management schemes for data center networks. These schemes operate in routers in the network and control which packets are sent or dropped in the order in which packets are transmitted. For example, DC-TCP provides low latency and high throughput. PDQ, RCP, pFabric, and PERC attempt to minimize slow completion times, and D-cubed and deadline-aware data center TCP attempt to meet deadlines. All of these schemes promise significant benefits for data center applications. However, in practice, it is very difficult to experiment with and to deploy these schemes in real networks. This is because most of these schemes require modifications to hardware routers, and developing new ASICs for routers is very expensive and time-consuming. Instead, researchers have developed a couple of approaches to experimenting with resource management schemes without deploying new hardware. In real networks, some researchers have used software routers to experiment with new resource management schemes. But to date, these approaches have provided limited throughput of only a few dozen gigabits per second, restricting experiments to only a few servers. Other researchers have used programmable software, such as FPGAs or programmable switching chips, to enable experimentation at line rate. But these approaches provide limited flexibility and require that your network is outfitted with the appropriate hardware in order for you to take advantage of them. The result of these challenges is that most experimentation with resource management schemes today is conducted using network simulators, such as NS. Unfortunately, software simulators don't fully capture the behavior of resource management schemes. First, they don't accurately model NIC features and network stack optimizations, such as interrupt coalescing, which can significantly impact protocol behavior. Second, they don't enable experimentation with real distributed applications, such as Hadoop or Spark, whose performance depend on other resources, such as disk and computation, in addition to the network. And finally, as anyone who's actually run one of these experiments using a simulator knows, simulations run incredibly slowly. Simulating only 1 second of time in a network can take hours. This slows down experimentation considerably. What this means is that no existing approach to experimentation with resource management schemes today provides accuracy, flexibility, and high throughput. This makes it difficult to prototype new resource management schemes and to evaluate the performance of existing applications under different resource management schemes. In this talk, we make two contributions. First, I will describe the key idea of whole network emulation. What this means is that we emulate the behavior of the entire network, including the resource management scheme, in a centralized software emulator, but then send the packets over the real hardware network. Second, I will describe Flexplane, a system that uses whole network emulation to enable users to faithfully experiment with resource management schemes on real data center networks. Flexplane provides three main properties. First, it is accurate, meaning that results achieved in Flexplane predict those achieved on real hardware. Second, it is flexible, enabling users to experiment with arbitrary schemes. In Flexplane, users express their schemes in C++. And finally, Flexplane provides high throughput. Our emulator prototype supports 761 gigabits per second of aggregate network throughput. In Flexplane, we implement the programmable data plane off-path. To achieve this, we augment the network with a software entity called the Emulator, which emulates the behavior of the network in real time. The emulator maintains a model of the network topology in software, and users implement their schemes in the emulated routers. Before each packet is sent on the real network, a corresponding emulated packet traverses the emulated network and experiences the behavior specified by the resource management scheme there. So how exactly does this work? When an endpoint sends a packet, Flexplane intercepts it before it is sent out onto the NIC and constructs an abstract packet. An abstract packet is a concise description of the packet. It includes the source, destination, and any other header fields needed by the resource management scheme. The endpoint sends this abstract packet to the emulator. Next, the emulator emulates the behavior of the network under the desired scheme in real time. It maintains an emulated network of routers and endpoints in software, configured in the same topology and with the same routing policies as the real network. Abstract packets begin at emulated sources and flow through the emulated network, encountering queuing delays and modifications such as ECN marks, as specified by the programmed resource management scheme. Abstract packets can also be dropped in the emulated network. Once an abstract packet arrives at its emulated destination, the emulator instructs the real endpoint to send the corresponding real packet immediately. If the abstract packet acquired any modifications, such as ECN marks, during emulation, the endpoint applies these modifications to the real packet before sending it out on the network. This ensures that the real packet arrives at its destination with the modifications that it would have in a real network that supported the same resource management scheme. If the abstract packet was dropped in emulation, the endpoint will drop the corresponding real packet instead of sending it. Because the emulator enforces bandwidth constraints, there will be sufficient bandwidth in the real network to transmit all admitted packets to their destinations. When the real packet traverses the real network, it encounters almost no queuing and no modifications, so higher layer protocols perceive that the packet is queued and modified by the resource management scheme implemented in software in the emulator. The reason that emulation over abstract packets works is that resource management schemes are typically data independent, meaning that they don't depend on the packet payload. They depend instead on a small number of header fields, which often comprise less than 1% of the total packet size. Each abstract packet is a concise description of 1 MTU worth of data, or around 1,500 bytes. It includes just the information needed by the resource management scheme, such as the source, destination, and any custom packet header fields. For example, to implement priority queuing in Flexplane, each abstract packet must include the real packet's priority. The purpose of emulation is to delay and modify abstract packets, just as they would be delayed and modified in a hardware network running the same resource management scheme. When abstract packets arrive at the emulator, they are enqueued at their emulated sources. They then flow through the emulated network, ending at their emulated destinations. As they flow through the emulated network, they interact with other abstract packets. They may encounter queuing delays, acquire modifications from the routers they traverse, or be dropped, just as they would in a real network. Thus, the emulator functions as a real-time simulator. One naive way to implement the emulator would be to simply use an existing software simulator, such as NS. However, this would run incredibly slowly. Instead, we implemented our own emulator, which differs from standard software simulators in 2 key ways. First, the emulator divides time into short time slots. The duration of a time slot is chosen to be the amount of time it takes a NIC in the real network to transmit the number of bytes represented by an abstract packet. Thus, in each time slot, each emulated port on each emulated router and emulated endpoint can send and receive 1 abstract packet. Time slots simplify emulation. Instead of individually scheduling each event, such as a packet transmission, at a specific time, as typical network software simulators do, the emulator only needs to ensure that each time slot, which can include dozens of these events, occurs at the correct time. In this way, Flexplane sacrifices a little bit of accuracy in exchange for running in real time. Second, the emulator only simulates the in-network functionality from the endpoint NICs onwards. We assume that any endpoint support needed by a resource management scheme, such as modifications to the TCP endpoint stack for DC-TCP, are implemented at the real endpoints. By leaving this functionality to the real endpoints, the emulator runs much more quickly, and the results more accurately capture real network behavior. To be a viable platform for experimentation, Flexplane must be accurate, meaning the results achieved in Flexplane predict those achieved on a hardware network running the same resource management scheme. To understand how Flexplane deviates from perfect accuracy, let's compare the latency experienced by a packet in a hardware network to that of a packet in Flexplane. In a hardware network running a given resource management scheme, the latency of a packet is the sum of the one-way unloaded delay, meaning the one-way latency in an uncongested network, and the one-way queuing delay. In an identical network that implements the same resource management scheme using Flexplane, packets still incur the unloaded delay and the queuing delay, but these now occur in the emulated network instead of in the real network. In addition, packets incur an additional delay for the round trip time to the emulator and back for when the real packet traverses the real network, and for any queuing delay encountered in the real network. Our emulator uses kernel bypass, reducing the round trip time to the emulator. The result is that, in practice, the latency in an unloaded Flexplane network is about 2.3 times the latency in an unloaded hardware network. Flexplane does not guarantee zero queuing within the hardware network. However, the emulation enforces bandwidth constraints, guaranteeing that there will be sufficient bandwidth to transmit all real packets admitted into the network to their destinations, so in-network queues cannot grow indefinitely. In practice, we found that these queues remain small, about 8 to 12 microseconds, when links are fully loaded. Flexplane exposes simple APIs to users so that they can easily write their own schemes. At the emulator, the implemented schemes are decoupled from the emulation framework. Users implement simple functions such as route and schedule in C++ at emulated routers, and the framework takes care of calling these functions at the appropriate times. Flexplane also provides a C API for reading and modifying packet headers at the physical endpoints. For schemes that require access to custom header fields, the user specifies how to copy these fields from real packets into abstract packets by implementing the prepare request function. Similarly, to modify packet headers after emulation is complete, but before the real packet is sent out onto the real network, users implement the function prepare to send. To enable useful experiments, the emulator must provide high throughput. To achieve this, the emulator runs on a multi-core machine and uses additional cores to scale throughput with the size of the network. Our multi-core architecture leverages the fact that network topologies are naturally distributed. We pin each emulated network component, such as a router or a group of endpoints, to a core. Abstract packets then flow between different cores via FIFO queues. With this architecture, router state is never shared between cores, and cores only communicate when their network components have packets to exchange. We implemented Flexplane by extending FastPass. The emulator is implemented using Intel DPDK for low latency access to NICs from user space. Support for Flexplane at the endpoints is implemented in a Linux kernel module, which functions as a Linux queuing discipline. We conducted experiments with Flexplane on a single rack of machines in Facebook's data center network. One server was set aside to run the emulator. Our experiments focus on evaluating Flexplane in terms of its accuracy, utility, and emulator throughput. To evaluate the accuracy of Flexplane, we compared its behavior to the behavior of hardware for 3 schemes that are supported in hardware today: Droptail, Red, and DCTCP. In this experiment, 5 senders send bulk TCP traffic to 1 receiver. All schemes achieve very similar throughput for the bottleneck link. Throughput is slightly lower with Flexplane because a small amount of throughput is reserved for abstract packets. During this experiment, we also sampled the queue occupancies in the hardware switch and in the Flexplane emulator every millisecond. We found that for each scheme, the queue occupancies in Flexplane were similar to those in hardware. The most noticeable difference between the two is that the queue occupancies in Flexplane tended to be slightly lower because of the effectively longer round-trip time in Flexplane. We also evaluated the accuracy of Flexplane in terms of flow completion time. We ran an RPC web search workload that includes a mixture of flows of different sizes. Request times were chosen by a Poisson process, such that clients received a specified load between 10% and 80%. We normalized the flow completion time for each flow by the average flow completion time achieved by a flow of the same size in an unloaded network when flows are requested continuously. This graph shows the results of this experiment for DCTCP, for the small flows on the left and for the large flows on the right. Our paper also shows these results for Droptail. Across DCTCP and Droptail, Flexplane predicts the average normalized flow completion time to within 2 to 14% for loads up to 60%. For higher loads, Flexplane's accuracy decreases slightly, but remains within 18% for small flows and 24% for large flows. These graphs also demonstrate behavior that is not visible in software simulations. For large flows, the normalized flow completion times at the lowest load are close to 1. This is what we would expect. For small flows, however, the normalized flow completion times remain above 2, even at the lowest loads. This unexpected behavior is due to the properties of real endpoint network stacks. In real endpoints, application layer latency depends on the rate at which packets are sent. When packets are sent at a high enough rate, the latency decreases significantly. For example, in one network, the ping latency dropped from 77 microseconds to 14 microseconds, when pings were sent every 50 microseconds instead of every 2 milliseconds. We observed this behavior across different networks and NICs. What this means for this experiment is that at low load, packets aren't sent frequently enough to attain the ultra-low latency that is possible when they are requested continuously, and the normalized flow completion times don't approach 1. This doesn't occur with large flows, which send enough bytes to fully occupy the NICs. This is an example of behavior that would be hard to accurately model in a software simulator, but is automatically captured by Flexplane. We have implemented and experimented with several different resource management schemes in Flexplane. We found that most schemes required only a few dozen lines of code in order to implement using the Flexplane APIs. For example, we implemented whole in 60 lines of code. Flexplane enables several forms of experimentation that aren't possible without it. First, we used Flexplane to compare the performance of different resource management schemes on a specific workload. In this experiment, we used an RPC-based workload that consists of a mix of short, high-priority requests and long, low-priority requests. Request times were chosen by a Poisson process so that client NICs were receiving at about 60% of their maximum throughput. This graph shows the trade-offs that different resource management schemes make on this workload. The x-axis shows the flow completion times for the long, low-priority flows, and the y-axis shows the flow completion times for the short, high-priority flows. The axes are flipped so that better performance is up and to the right. For this simple workload, priority queuing achieves the best performance. Droptail performs well for long flows but poorly for short flows. At the other end of the spectrum, Hull displays the opposite behavior. This experiment demonstrates how Flexplane enables users to compare the performance of different resource management schemes in a real network, even for schemes that are not supported in hardware today, such as pFabric and Hull. We also used Flexplane to evaluate how new resource management schemes affect the performance of an unmodified distributed application that uses both network and CPU resources. For this, we ran 2 different Spark applications, using Flexplane to implement DCTCP, Hull, and Droptail. In the sort application, which includes multiple waves of small tasks and small data transfers, both DCTCP and Hull yielded small improvements in completion time over Droptail. In contrast, in the coordinate descent application, which primarily sends large bulk data transfers, the application experienced a slightly higher completion time with DCTCP and a significantly higher completion time with Hull because of these schemes' more aggressive responses to congestion. Because both of these Spark applications spend the majority of their time performing computation, it would be very difficult to accurately model them in a software simulator and to conduct this experiment in simulation. Finally, we measured the maximum sustainable throughput of the Flexplane emulator. In this experiment, we used 2 cores on the emulator machine to generate the workload, and another 8 to run the emulator. With all 10 cores and a topology of 7 racks, the emulator achieved a total throughput, aggregated across all routers in the network, of 761 gigabits per second. Thus, the emulator could support a network of 224 servers, each sending at an average rate of 2.5 gigabits per second. We also evaluated the throughput for different emulated network topologies. All topologies included one aggregation switch connecting 2 or more racks of machines, such as this topology. This graph shows how throughput scales with the number of cores used in the emulator. The smallest configuration requires 3 cores, 1 for the aggregation router and 1 for each of the top-of-rack switches and their corresponding endpoints. In this experiment, throughput falls short of linear scaling based on the throughput of a single router and its endpoints. To understand why, we measured the throughput of topologies with up to 8 isolated racks of servers with no communication between racks. The throughput in this case is much closer to linear scaling, demonstrating that the shortfall from linear scaling in the case of connected racks is primarily due to the communication with the core running the aggregation switch. The Flexplane emulator significantly outperforms software routers in terms of throughput. For example, the RouteBrick software router provides 35 gigabits per second of total throughput with 32 cores. If we compare throughput per clock cycle to normalize for differences in number of cores used and differences in clock frequencies, we see that the Flexplane emulator achieves 81 times as much throughput per clock cycle as RouteBricks. This is because the Flexplane emulator only processes abstract packets, allowing it to maintain a small memory footprint. All of the memory used in this experiment fits in a 30 megabyte L3 cache shared by the 10 cores. In contrast, RouteBricks applications access 400 to 1,000 bytes from memory for each packet processed. In summary, I described the idea of whole network emulation in a centralized software emulator and presented Flexplane, the first system to use whole network emulation to provide accuracy, flexibility, and high throughput, and to enable experimentation with real applications such as Spark in real networks. Thank you, and I'm happy to take questions.
Chow from the University of Washington. I was wondering, have you compared directly with NS3 in terms of accuracy or simulation speed? Because in the normalized FCD graph, you only have 2 lines, the hardware and the Flexplane.
Yeah, so I didn't run an explicit comparison with those simulators myself, but we did, in the paper you can see we reproduced an experiment that many other researchers have produced in NS2. And basically, our results demonstrated the same trends, except for that detail that I showed with the flow completion time results, where in software simulations, you see that flow completion times go to 1 for small flows, and we didn't observe that.
In the NS simulation, you meant?
Yeah, so in the NS simulation, previous works have observed that flow completion times approach 1 for low load for small flows, but we didn't observe that. They remained high, as I explained earlier.
Okay, thanks.
Hi, Liu from Microsoft. So when you emulate the network, are you using the real big-scale data center topology? And how much resource do you need to emulate a large scale?
Sorry, so am I using the real, what was the next part?
Yeah. I mean, yeah. So I mean, the network you emulate, is it a real-world large-scale network or a testbed network that for you to justify the allocation algorithm?
So for our experiments, we focused on small network topologies, but they were reasonable network topologies.
Okay, so is your emulation can cross distributed servers and so to make it really large scale? I mean. Yeah,
so you can run across larger networks as long as you stay within this throughput constraint that I talked about. That the emulator today it can support multiple racks of machines, but our current implementation only scales up to 761 gigabits per second of aggregate throughput. That was only with 10 cores. You could imagine trying to scale this to use more cores and then to support larger networks with more throughput, but we didn't do that for this work.
Okay.
Hi, Rob McGinnis from UC San Diego. Have you looked at all at the potential effect of this on application completion time, specifically for applications that have large amounts of either RPCs that go back and forth, where the initial latency increase on the flows themselves kind of builds up over time as these flows get completed, and there's just a lot of flows starting throughout the lifetime of the application?
Yeah, so I think in an application like that, what you're going to see is, since Flexplane does add this latency, that basically it's as though you're running on a network that has a slightly larger round trip time. So that will be the result that you see there.
Have you looked at results for that at all, and did it adversely affect any sort of applications you looked at?
I can't think of any specific applications that we ran that fit the model that you're describing.
Thank you.
Mothi. Hi, Mothi, ETH Zurich. So back in the sort of good old days when people wanted whole network emulation and wanted to run real applications and actually real network stacks and things, they would use something like ModelNet with Emulab, which would do full network emulation, and you could put in sort of schemes and things like that. I mean, do you see other kind of ideas from something like ModelNet that you think might be relevant to Flexplane, in terms of how it was doing its work?
So my understanding with ModelNet is that they didn't use this idea of sending a short description of the packet. They actually sent the whole packets.
No, they sent a short description of the packet. It was just a compressed header because they didn't need the payload.
Okay. Yeah, so in that case, that aspect sounds pretty similar to what we've done here. I don't know that work well enough to comment further on that.
Okay.
All right, let's thank Amy, and let's thank all three speakers from this session.